Yes, at least the first two speakers are here already, so maybe we can start. Okay, so welcome everybody to the first session on probability logics. I'm Enrique Miranda. Well, I would like to start thanking the organizers of the conference for all the work, well, particularly doing all the work for making the online and also in person, which is like twice as much. So it's much appreciated. We have four talks here, as you can see, I'm online. So what I will do is that if there is anybody questions after the presentations, okay, you can let me know. For those online, you can ask questions through the chat. And then you have 15 minutes for the presentation, 5 minutes for questions. So when you have done 13 minutes, I will be showing this.
Okay, perfect.
And then when you are when you have done 15 minutes, okay, I will be showing you this.
Okay, perfect. Thank you.
Okay. So the first speaker, the first paper is going to be Algebras of Sets and Coherent Sets of Gambles by Ariana Casanova, Jurg Colas, and Marco Zafalon from Switzerland. And it's going to be Ariana making the presentation.
Perfect. Thank you, and thank you for this opportunity. Okay, so perfect. Okay, I present Algebras of Sets and Coherent Sets of Gambles, that is a joint work between Istituto Dalle Molle di sull'Intelligenza Artificiale and the Department of Informatics of University of Fribourg in Switzerland. So essentially in recent work, we have shown that coherent sets of gambles that are the main tool of desirability theory, that is a general framework for to manage uncertainty, form an instance of...
Sorry, Ariana, can you, yes, because I think there is some echo and they're trying to sort that out, if you can wait a few seconds.
Yes, okay.
Sorry.
Okay, Enrique, I think you can start.
Okay, perfect.
I tried to mute.
Okay, so as I said before, in recent works, we have shown that coherent sets of gambles that are the main tool of desirability theory, that is a very general framework to manage uncertainty, form an instance of information algebras, where information algebras are instead algebraic structures to manage information. So essentially, in this view, coherent sets of gambles are seen as pieces of information. Now we have extended this work, finding some connections between this information algebra that is constructed starting from coherent sets of gambles and some instances of set algebras that are prototypical forms of information algebras. So now I will remember some preliminaries about the two theories, so desirability theory on the one hand and information algebras theory on the other end. And then I will focus instead on the main results of our work. So desirability theory can be seen as a generalization of the Finettius one, in which instead of having a unique probability distribution, we work with sets of probability distributions. And to better understand the situation, we can proceed with an example. So let us start with the concept of gamble, that is a generalization of bets of the Finetti. So suppose to bet on the possible height of Albert Einstein. So suppose to create a set of possible heights that goes, for example, that is, for example, composed by all the real values that goes from 1.5 meters to 2 meters. Then a gamble over this set is a bounded real valued function that can be interpreted as an uncertain reward. So for example, if an agent is disposed to accept the gamble that you can see on this slide, he is disposed to win essentially 0.75 units of utils in the case in which the real height of Einstein was 1.8 meters, and is disposed to lose instead 0.75 units of UTIS in the case in which instead the real height of Einstein was 1.63 meters. Clearly, an agent is disposed to accept this gamble or not, depending on his beliefs on the possible heights of Einstein. There are some gambles that must be always acceptable because they can increase the wealth of an agent without the risk of decreasing it. And these are, for example, these one that are part of a class of gambles, a class of non-negative gambles. And on the other end, instead, there are the opposite class that must always be rejected because the gambles that are part of this class can decrease the wealth of the agent without the possibility of increasing it. So more formally, we have that a gamble is a bounded real valued function defined on a possibility space that can be interpreted as an uncertain reward in a linear utility scale. And a coherent set of gambles is essentially the set of gambles acceptable for a rational agent. So it must contain the not negative gambles, must have empty intersection with the opposite class, and if the agent is disposed to accept two gambles, he must be disposed also to accept their sum and their multiplication for a positive scalar given the linear utility scale. There is an important class of coherent sets of gambles that are the maximal ones, that are coherent sets of gambles that are not proper sets of other coherent sets of gambles, and that are characterized by these properties. So a coherent set of gambles D is maximal if and only if for all gambles that are different from zero, or this gamble belongs to this set, or minus this gamble belongs to the set. There is also a connection with the probability. Indeed, starting from a coherent set of gambles, we can construct a lower and an upper prevision for every gamble that corresponds to the supremum buying price and the infimum selling price that the agent that fixed this coherent set of gambles is disposed to set for that gamble. And it is possible also to show that they correspond to a lower and an upper expectation. And so in particular, they are in a one-to-one relationship with closed and convex sets of probabilities. Moreover, there is also a connection with some elements in logic. Indeed, we can see that there is a correspondence between some elements in desirability and some elements in logic, where in particular, coherent set of gambles corresponds to consistent and closed sets obtained respect to the consequence operator that is the natural extension operator. Finally, it is possible also to construct a connection with the preference relation. Indeed, starting from a coherent set of gambles, we can say that a gamble F is preferable to a gamble G if essentially the agent that corresponds to that set is disposed to buy the gamble F and sell the gamble G. So essentially he is disposed to accept their difference. So we have seen that the desirability theory is a general formula used to manage uncertainty because it is part of imprecise probabilities and it is linked in particular to upper and lower previsions and clear sets that are closed and convex sets of probabilities. It is a simple formalism to work with. It is based on an idea of rationality that essentially corresponds to consistency of beliefs of an agent. It has some links also with logic and with preference relations. On the other end, instead, we have information algebras that are algebraic structures to manage information that are based on the key ideas that essentially information comes in pieces that possibly refer to different questions. Then all these pieces can be aggregated together to obtain the whole amount of information. And then also the information about a specific question can be extracted. And this leads to an algebraic structures that satisfy some axioms. In particular, it is possible to show that we can construct an information algebra also starting from logical systems called information systems that can be constructed by a language, a consequence operator, and a class of sublanguages that represent the possible questions. In this case, the information algebra is composed by pieces of information that corresponds to the closed sets, closed respect to this consequence operator, that can then be combined, aggregated together with an operation called combination, and from which the information that regards a specific sublanguage can then be extracted with an operation called focusing. Essentially, the main idea of our work is to show that desirability forms a logical system of this type, in which the language corresponds to the set of all gambles. The consequence operator is essentially the natural extension operator, and the pieces of information corresponds to the consistent one, two coherent sets of gambles, and the only inconsistent one to the set of all gambles. Moreover, clearly the vacuum information is represented by the non-negative gambles. This leads to an information algebra where the pieces of information are the coherent sets of gambles that we call information algebra of coherent sets of gambles. The advantages of this reformulation of desirability are essentially that we obtain a new algebraic representation of desirability that allows us to abstract what are the properties of desirability that are not properties of desirability itself, but of these macrostructures to manage information. And it can be useful to treat some problems, such as, for example, the compatibility one, that is the problem of establishing if some probabilistic assessments have a joint probabilistic model treated with the framework of desirability. And also we think that it can also simplify the introduction of probability and also imprecise probabilities into the information algebra theory. In the current work instead, we extended the previous one, showing that we can find some connections between the information algebra of coherent sets of gambles and some instances of set algebras, where set algebras are prototypical form of information algebras in which the pieces of information corresponds essentially to set of possible answers to questions that can then be manipulated using the usual set operations. And in particular, we have shown that it can be constructed as set algebra from the subsets of the possibility set on which gambles are defined, and that this set algebra is embedded into the information algebra of coherent sets of gambles. And on the other end, the information algebra of coherent sets of gambles itself can be embedded into a set algebra composed by sets of maximal sets of gambles. So these theorems remind us the Stone theorem for Boolean algebras. So an idea for a future work is to try to extend these results also for other types of information algebras using the general formalism of our paper, because we have already some results of this type, but in the particular case in which the questions of interest regard the values of some set of variables. Instead, here in our paper, we model the questions as general partitions of a universal set, in this case, the possibility set on which gambles are defined. And moreover, we want to also to try to extend our work to lower previsions and previous sets, because also here we have some results in the previous case in which the questions represents the questions are interested in the values of some set of variables, in which we have shown that also coherent lower previsions form an information algebra, and so we want to try to extend also these results in our more general framework. Thank you for the attention.
Thank you so much, Ariana. So now, if there are any, okay, you don't hear it, but they are clapping at you, Ariana.
Okay, thank you.
So if there is anybody from the room who wants to ask a question, or anybody online, if you go to the part of reactions in the chat, next you can raise your hand.
Okay. So,
Yeah.
I don't know whether Ariana hears me.
Yes, a bit.
Okay, so I will. So in your presentation around page 13 or 15, you mentioned consequence operator.
Yes.
And I wonder what are algebraic properties of this operator, whether it's a usual closure operator in a sense of algebra, abstract algebra, that means whether it's extensive, monotone, and idempotent, whether these are the properties.
Yes, the fact that essentially a set is always contained in its closure. If a set is a subset of another set, then the closure of this set is contained in the closure of the other. And the closure operator applied to the closure of a set is again the closure applied to a set.
Okay, thank you.
Thank you. Any more questions? Or questions from the chat? Okay, yeah. So in the chat, Jasper de Boek has a question. So Jasper, you can go ahead.
Hi there, can you guys hear me?
Yes.
Yes.
Okay, great. Ariana, you listed at some point the advantages of studying sets of desirable gambles in this framework, and they're mostly about connecting these fields. I was wondering, is there from an IP perspective, does this come with a power, a useful power, in the sense that do they, for example, have algorithms that can automatically deal with inferences and these kind of things that we can use from information theory? Does it come with an advantage in that sense as well, or should we at this point mostly see it as a theoretical connection between the fields?
At now, we have seen also only the theoretical perspective, but information algebras are also born to generalize the local computation schema to other uncertainty formulas in respect to probability. So maybe also this connection can be useful for desirability. But we haven't already worked on it, so I don't know exactly the details of these possible connections.
Okay, thank you. That would definitely be a nice thing to look at, I think, because doing actual computations with desirability is no small feat, and if we have a new framework we can use for that, that would be very nice, I think. Thank you for your presentation and for your
Thank you.
I guess that the structure of the reasoning could be taken from information algebra, but I suppose the question is whether it's possible to have an efficient way of implementing the two basic operations of combination and projection. I suppose that so I suppose that's the key thing. If a certain class of a problem, there's going to be an efficient way of implementing those, then it could be useful as a
yes, exactly, yes.
Okay. Any other questions or comments? Okay. Well, I just have one last question, Ariana. So, well, you say that you have this representation of sets of desirable gambles, which are super general as information algebras. Okay, but there are some models like, well, the sets of desirable gambles sets that Jasper de Boek uses with the choice functions. Well, or for instance, also you have some work on nonlinear desirability. Nonlinear, yeah. So do you think this could be also embedded in information algebras or not?
Maybe yes, but I must think about it. But
okay.
Maybe yes. If we can construct another consequence operator to obtain a coherent set of gambles with an enlarged definition of coherence, maybe yes, we can reproduce the entire reasoning.
Okay.
Also for other cases.
Well, that would be very nice. All right, so then we thank Ariana again.
Thank you.
Okay, I applaud you virtually, Ariana. The next speaker will be online, will be, I think, Jürgen Landes, and he's presenting the work entitled Attributable Uniqueness of the Maximum Entropy Approach.
Nice, thank you. Share the screen.
Okay, perfect.
Shall I start, or shall we wait 5 more minutes as it says in the program?
No, I think you can start.
Okay, so thank you very much. Thank you very much for listening to me. Thanks to the organizers for putting this all together. Yes, so now we'll be speaking about the maximum approach. So I'll just give you a brief outline of the talk. I'll start out with an introduction, tell you what the problem is all about. Then I will speak about the maximum entropy principle, the maximum entropy approach to infinite languages. Then I'll have some results, and in the end, some conclusions. And as usual, I speak very quickly. I'll try to calm myself down. So introduction, here we go. The general picture is, well, we want to know how strongly should we believe things if we are rational agents. And of course, this is a very wide question. And here's a very first answer. Well, it of course depends on what the information you have. It depends on the available information. If the information is very good, that means then you believe some other things than if the information is very bad. The second answer, maybe a little bit more interestingly, in interesting cases, beliefs can and are modeled by probabilities. So if your information is such that you actually know what is the case, this is not really interesting because then you just know what's going on. So in interesting cases, we use probabilities, or in this community, sets of probabilities to model our beliefs. And now this is a talk in the framework of precise probabilities. So I'm not working on imprecise probabilities. In case there is more than one probability function, which is consistent with the evidence, we need something more to nail down a single probability function that we want to use for inference, representations of beliefs and decision-making and so on and so forth. So in case the evidence doesn't nail it all down, we need some further restraining. Okay, and the framework I'll use to tackle this, this problem in the general picture is that of inductive logic. And there's no time to motivate this here. I just tell you what the framework is and then off I go. So we start out with the first order language L. So first order logic, we have a language L. The language contains some constants T1, T2, T3, and so on and so forth, countably many. And these constants are supposed to exhaust the universe. So we have a constants for everything we can talk about. We also have in our language relation symbols. So this is R1, R2, and so on. You have the usual connectives and or a negation and the quantifiers. However, importantly, in this language, you do not have function symbols, and we also don't have a symbol for equality. So this is the language we're going to use to represent the things we want to reason about. And then to model our beliefs, we define a probability function P over the sentences of L in the usual way. So it needs to satisfy the usual axioms. Again, no time to go into that. Now, we also assume that we have some evidence or premises if you're a logician. And the premises here take some probabilistic form. So we have our first part of the premise is the sentence phi1. This is the sentence of the language. And this sentence phi y is assigned some probability, so P of phi1. And that is not just necessarily a single value. Say the probability of phi1 is 20%. So that, but in this case, it could be that the probability of phi1 is somewhere between 20 and 30%. So the probability of phi1 is in some interval xi. And so on, can have that there are multiple premises. Each of these premises says, well, this sentence has a probability within some range. And to make things easy, you will assume that all these x1 up to xk, that these are intervals, so compact sets of the unit interval. And then the question is, we are trying to answer in inductive logic, which probabilities to attach to a sentence psi of the language. So psi is the thing we're now interested in. And this is the way we formalize it. So we have some kind of inductive entailment relation, which is denoted by this squiggly entail. And on the left, we have our premises phi1 up to phi k, and we assign some probability intervals to them. And then we want to know which probability or which probability interval attached to psi. And as I said, I'm working with sharp probabilities, so this psi is going to be a single number. The question is, for an arbitrary psi, which single number should we put here? So this is the framework of inductive logic I'm using to reason about these things. Now, as I said, sometimes the evidence isn't strong enough to nail you down to a single probability function, and some further constraining is necessary. And this is where the maximum entropy principle comes in. In case there is more than one probability function consistent with the evidence, further constraining is necessary. And the maximum entropy principle now says, well, look at all these probability functions that are actually consistent with your evidence, and then use the one which maximizes Shannon entropy. And Shannon entropy is given by this formula here. If you've never seen it, let me just tell you that this is some kind of expectation over here, because it's omega alpha states, and then it's multiplied by the logarithm of the probabilities, which has something to do with information theory. This is all I want to say about this. The maximum entropy principle says, pick the probability function which looks okay, but the one which has maximum entropy. Now, on finite domains, and this is really important for the purposes of this talk, this is very well defined. It's just an optimization problem you need to solve. On infinite domains, this thing is much, much harder, because if your sum here is infinite, it can very well happen that many, many probability functions have an infinite entropy. Now, the maximum entropy principle tells you to pick the function with maximum entropy. But if you have multiple probability functions which all have infinite entropy, how can you say that one of them has more entropy than the others? And this is the difference where the infinite case and the finite case come apart, because on the finite case, this just cannot happen that you have an infinite amount of entropy. Okay, and here's where the maximum entropy approach comes in, which applies the maximum entropy principle. So this thing here on infinite predicate languages. And it starts out with this notion of an n entropy. So what you do is you look at the language ln, which is just the language you get when you look only at the first n constants. Then you look at the states you can build with those first n constants, and you can define entropy there. You just look at the first initial bits, kind of. And this then gives rise to the notion of the n entropy. Okay, so of course, this is just kind of a snapshot of the entropy of the whole probability function, which is defined on the entire language. And then the idea is, of course, that you somehow glue all those snapshots together and come up with a notion of entropy overall. And this approach says P has greater entropy than Q. Now, this is the real thing. This is what we're after. Intuitively, if eventually P has greater entropy than Q. Formally, that says if and only if there's some natural number, so this is a lower bound, such that for everything above this lower this bound, the n entropy of P is always strictly greater than the n entropy of Q. And that's denoted by P suc Q here, the successor. And now we can use this to define an inductive logic as follows. We need one more bit of notation, and this is the set E. These are just the set of probability functions consistent with the evidence. So this is your feasible set. This is in the set which you would want to pick. Certain forms of imprecise probabilities just end here. They say, well, yeah, this is the set, and that's all fine. But then the max end approach says, well, no, you have to pick a particular one in there. And the maximum entropy approach now explicates this idea as follows. Max and E are all those probability functions in E, such that there is no Q in E which has strictly greater entropy than P. So this is everything that is not dominated in entropy. And these are the ones you should use for inductive inference. And in order to make this all well defined, you better hope in this set there's only a single element, because otherwise we can't attach a single probability to sentences. Okay, that's the definition of the maximum entropy approach. Now I want to talk to you about two alternatives to this approach. And they arise from looking at different ways of comparing entropies. So remember, we said that P has greater entropy than Q. So overall, if and only if there's some natural number n, such as for everything above this great number n, it holds that the n entropy of P is strictly greater than n entropy of Q. That sounds very reasonable. But why on earth did we insist on strict equality? Why wasn't greater or equal then good enough? Furthermore, you could say, well, I say you could even relax that and say, well, something in between. Well, there are infinitely many n, such that this is strictly greater, but from this n onwards, from this capital N onwards, it always has to be greater or equal than. And if you ask me, and ask me before I've done all this work, so which of those looks good to you? And I'll say, well, yeah, I don't know. They all look very reasonable. I can't give you a principled ground of why you should prefer the first alternative or the second or the third. It all looks very reasonable. So with these notions of comparing entropies between probability functions in hand, we can actually define the maximum entropy functions according to these relations of defining which entropy is greater than. And we can just do the same game again, and then we say, well, the maximum entropy functions in E, according to this greater than relation, are those which are not dominated in this by this relation. And again, all of these three look completely reasonable. I cannot tell you which is better or which is worse without just doing any hard math. This all looks very, very plausible from a maximum entropy point of view. Now here come the relations, the results, and the results are good news. So if our set E of probability functions is consistent, so we have is non-empty, so we have consistent information. And if the set is convex, I'll talk about the convexity later. If at least one of those three maximum sets of maximum entropy functions, so there's these guys here, yeah, these are the ones we are really, really interested in. As long as one of these three is a singleton. So remember, I'm working in the framework of precise probability. This is exactly what you want. You want a single probability function that tells you everything there is to know. So in case at least one of those three is a singleton, then all the other two are the exact same singleton probability function. So that says, in these cases, these three approaches do not disagree. They always give you the same probabilities for inference. Now, short side note, I said I'd come back to the convexity of the set of probability functions consistent with the evidence. As long as your constraints are the way I set it up, namely that those xi are non-empty intervals, this set E will be not empty and will be convex. In case of non-convexity, all bets are off anyway. So what maximum entropy approaches do is try to get a probability function which is as close as possible to the flat distribution. But imagine a situation where you have the flat distribution and the probability functions you want to look at are arranged around in a circle around this middle point. This midpoint is the flat one, and the things you could pick are in a circle around. And then you're supposed to pick the one which is closest to the middle. And of course, this is utterly impossible. This is why the convexity assumption is always so important. But in this case, I'm looking at those xi are all non-empty intervals, compact sets, all is good. Furthermore, I'd like to talk to you about a result I recently obtained together with Surush and John, which is not in the paper, but is forthcoming, and that's the following. Now we're on the case of a single premise. So we have a single premise, and we believe, our premise says, well, believe phi with some number c, as long as c is not 0. Yeah, so believe it to degree 1, 50%, 25%, whatever. Someone says phi has probability 25% to you, and then you're wondering, okay, which probability function should I use for inference? And we should also assume that the prior probability of phi is non-extreme. So that says that the uniform probability function defined over L assigns phi a probability which is not 0 and not 1. In that case, there is a single maximum entropy function, and by the previous result, it doesn't matter which of the three approaches you take. And this probability function is just the uniform probability function, Jeffrey conditionalized by the premise you're given. It's just c times the flat probability function conditionalized on phi plus 1 minus c times the flat probability function conditionalized on not phi. So, in words, for a single uncertain premise with non-extreme prior probability, max and updating is just Jeffrey updating. And that's really, really cool because this wasn't really known before. So it was really, really hard to envision what's going on in many, many cases. But now we can at least say that in cases where we have kind of an idea what should be happening in the finite case, namely that updating should be Jeffrey updating, we get the same result for infinite predicate logic languages. And there's a simple corollary. If we have a single certain premise, so C equals 1, and of course we cannot assign this phi probability 0, then max and updating just collapses to Bayesian updating, just because Jeffrey updating collapses to Bayesian updating. So we have found a large range of cases in which there's just one single max and updating. Now I should be challenging my inner Lord of the Rings fan to rule them all. Really, there is just one of them, and this is we feel is really, really cool. Now this is the positive side of the story. Now to the dark sides. And these are the zero prior premises. Now I'm talking about premise sentences which have zero prior probability. Let's consider a particular one. The premise sentence is there exists an X such that for all Y are XY. And it turns out that the set of probability functions which have maximum entropy for this premise are all empty. Because every probability function you have, you find another one which has greater entropy. And so there are no maximal sets in this element, and therefore this thing is empty. Now, continuing in the spirit of this entire approach I've taken during this talk, the idea would be a natural idea to try to come up with some way of finding some functions for probabilistic inference is to modify the notion of comparative entropy. So I've showed you the original one and then two modifications. And the idea is, of course, well, let's try a fourth one. Well, what's the most simple thing you can think of? Well, we could just say P has greater entropy by Q, and this is now denoted by P square brackets, curly brackets Q, if and only if the n entropy of P is always greater than the n entropy of Q, from some point onwards, maybe. We just say straight up, well, you have to be greater all the time. And then we can define inductive logic in the usual way. This now gives us the set of maximum entropy functions according to this relation. However, it turns out that in many cases, not always, but in many cases, the set of maximum entropy functions are just all the functions which are consistent with your evidence. So that means, well, just pick anything. And that doesn't really make any sense, and it doesn't give us a good answer for in the framework of precise probability where we want to have a single probability function. So that's the bad result because, well, yeah, we still don't really know what to do here. The obvious try failed. And of course, you know, if you have a good idea of what to do here, please let me know. And being a philosopher, I now come to offer you some conclusions. So I think the uniqueness of the maximum entropy approach, so that these three things are really all the same, is quite noteworthy in light of Stringer's results suggesting and comparing different notions of entropy, different forms of maximization, which always lead to different maximum entropy functions. There's really a bunch of literature which says, well, if you use this and if you use this and use that, you get always a different maximum entropy function. Here, the opposite happens. Everything collapses to a single maximum entropy function. Going back to the bad results, updating with evidence of zero prior probability remains hard, also remains, as in the infinite case, remains hard. If you want to just do Bayesian updating with zero prior probability events, you know, your head is just going to explode. This is just, it's just not defined because you can't conditionalize on something with probability zero. And somewhat related problems appear in the infinite case. Nevertheless, in the infinite case, we kind of need an answer because the premise I've showed you here, well, okay, it has zero prior probability under the uniform prior, but it's not necessarily, this is not a contradiction. This sentence phi is utterly contingent. This might very well be. So if someone now tells you that this thing is really true, you should have some way of setting your probabilities accommodating this kind of premise. And it's unclear what to do in this case. And this is, of course, something, you know, someone who has a good idea, please come forward with it and do something about it. To address this problem, I think we can't really draw on the finite setting because there, whenever we have a contingent premise, the uniform probability function will give us non-zero probability.
Yeah,
and wherever we have something which has zero probability, it is actually an inconsistency. So drawing from the infinite, from the finite setting will not be that easy. And finally, I'd like to.
Yeah. Sorry, it's the time is almost done.
This is my last point.
Okay.
I've always multiple uncertain premises seem to really pose hard questions. Thank you very much.
Okay. Okay. Thank you. Sorry. So if there are any questions there in the audience.
Okay, I have a question.
Mm-hmm.
I missed your definition of this well, some details of your definition of n entropy.
Yeah.
You have this omega n, and my question is, so it's a kind of approximation of the infinite omega. So is it like partition of that omega, or is it like subset which grows, finite subset, which covers omega in infinity? I mean,
So these are you familiar with the notion of state description or end states? State description?
I don't know. No.
So this is everything you can describe with the first n constants.
Okay, so it's like more subset of the.
Yeah, so it's like if you would like to talk about infinite states, you just say what everything is true, and this is just the first bits of all these infinite strings.
Okay. Thank you.
And in these kind of, if you push this to infinity, then this is kind of an approximation of the entire language, kind of.
Okay, any further questions in the room? Or if it's from the chat, you can raise your hand.
There's something I was wondering about for the for that last issue you had with the probability zero. Could you do a similar kind of construction as you were using earlier as you were tending n to infinity, but start off with probability of epsilon, probability being less or equal to epsilon, and tend epsilon to zero, and have dominance where for all sufficiently small epsilon, one is better than the other. Could something like that work? Have you thought of anything like that?
Yeah, so for this particular premise, the problem is that every end state is consistent with the evidence. You can just make it true because these are quantifiers, and you can just postpone the truth making of this to ever later stages. So at every finite stage, the uniform probability function is actually consistent with your evidence. And since it's uniform and as flat as possible, and it has maximum n entropy. So for all n, the uniform probability function has maximum n entropy. The problem is this thing does not satisfy the premise because it gives the premise probability zero. But we have been playing around with this and sneaking in an epsilon somewhere and saying, well, we just need maximum n entropy up to epsilon or something like that. This is something we have been thinking about. We haven't come up with anything clever yet.
Okay, any other questions? Yeah, actually just one last comment from what you were saying. I was wondering if maybe in the book of Peter Woolley there would be something interesting, because also there he's considering like, well, you could have like things defined on a finite set or extensions of a finite set or extensions of uniform things to infinite spaces. And you could maybe avoiding the zero problem there, or considering, for instance, the models of sets of desirable gambles that Ariana Casanova was mentioning in the first talk, because in those cases you avoid problems with conditioning on probability zero. I don't know, maybe there is something there that could be useful.
Hopefully.
Okay. Okay, so we thank Jürgen. Okay.
Thank you.
Okay. And the last talk would be the paper by Nicky Pfeiffer and Giuseppe Sanfilippo, Interpreting Connective Principles in Coherence-Based Probability Logic. And actually, Giuseppe Sanfilippo is in Prague, but I think it's Nicky Pfeiffer who is making the presentation online.
Yes, so, okay, so thank you very much. This is joint work with Giuseppe, and we are going to interpret connective principles in coherence-based probability logic. Can you see the screen moving? Is it now on the second page?
Oh, yes.
Okay, thank you. So the outline is first some introduction, and then I will present two approaches that we developed in order to model connective principles. So first, what is connexivity? The basic connective intuition is that conditionals of the form not A, if not A, then A, so self-contradictory conditionals, that they should not hold. This is intuitively plausible, right? If it's raining, then it's not raining. It sounds very strange. And it also matches the experimental data. So we did some experiments on this. But under the material conditional interpretation of conditionals that is used in logic, however, it holds that these sentences are contingent. So if not A, then A is logically equivalent to A. We aim to cover this basic connective intuition that these sentences, these self-contradictory sentences, are false by the observation that for any event A, which is not self-contradictory, not a tautology, it is necessary equal to 0. So 0 is the only coherent value. So this matches the intuition. And now we are going to model these connective principles. So the motivation is to interpret and check the validity of connective principles within coherence-based probability logic. And we are going to do that by two approaches. In the first approach, connective principles are obtained by defaults interpreted by probabilistic constraints on conditional events. That is, basic conditionals are interpreted by probability constraints, and negation of the assessment is considered. And we are going to use the wide scope negation. In the second approach, however, connective principles are obtained by logical operations on conditional events. So here, basic conditionals are interpreted by conditional events and not as constraints. And here we negate the object, and we use the narrow scope negation. So what are the then connective principles? Here is a list of connective principles used in connective logics. Not all are valid in all the systems, but these are the main principles, and we are going to study these principles. So for example, Aristotle thesis, it is not the case that if not A, then A. Or here, these are iterated ones. If A, then B, then it is not the case that if not A, then B. So the first approach, here we interpret the basic conditional if A then C by a default. So C is a plausible consequence of A, which we interpret by the conditional probability assessment of C given A equals 1. The negated conditional is interpreted correspondingly as a negated default, which we interpret by the wide scope negation. And that is given by just saying that the corresponding conditional probability is not equal to 1. So we interpret the inner negation not A by the overbar, then the conditional is interpreted by the default not C is a plausible consequence of A, and likewise as it is written here. So we first consider non-iterated connective principles, that is where the key connective is not conditional, and we define it as follows. A non-iterated connective principle is valid if and only if the probabilistic constraint associated with the connective principle is satisfied for every coherent assessment on the involved conditional events. So the validity of Aristotle thesis, for example, is given as follows. We interpret Aristotle thesis by the negated default. A is plausible, is not the plausible consequence of not A. That is, the conditional probability of A given not A is not equal to 1. We observe that A given not A equals 0 is the unique precise coherent assessment on A given not A. Then this satisfies the probabilistic constraint associated with our connective principle, and therefore Aristotle's thesis is valid. The validity of AT prime is done in a very similar way. For Abelard's first principle, which is this one, it is not the case that if A then B and if A then not B. This is interpreted by the negation of these two defaults. That is, the conditional probability of B given A equals 1 and the conditional probability of not B given A equals 1. So this assessment is not satisfied. And this principle is valid because coherence requires that these two probabilities need up to sum up to 1. So therefore, this is Abelard's first principle is valid. Aristotle's second thesis, which is, it is not the case that if A then B and if not A then B. So see, this is very similar to this one, but here we negate the consequent and here we negate the antecedent. It is interpreted by the negation of this set of defaults, which is interpreted probabilistically in this way. And we see that this is not satisfied because if you assign B given A equals 1 and B given not A equals 1, which is perfectly coherent, then you have an instance where you see this is not satisfied. So therefore, Aristotle's second thesis is not valid. For checking iterated connective principles, we need to give another definition, and this is as follows. An iterated connective principle from where we have some conditional here and some conditional here is valid if and only if the probabilistic constraint of the conclusion is satisfied by every coherent extension from the premise to the conclusion. So this is not p-validity, but this is rather this, again, satisfaction of the constraints. And here, for example, look at Burst Thesis, which is this principle here. This is interpreted that if the conditional probability of B given A is 1, then the conditional probability of not B given A must not be 1. And this is valid because not B given A must be 0 when B given A is 1. Therefore, Burst thesis is validated. And also Burst thesis prime is also validated in a similar way. However, reversed Burst thesis and these variations B3 and B4 are not valid. Let's go now to the second approach. Here we, instead of interpreting basic conditionals as defaults in terms of probabilistic constraints, as we have done in approach 1, we now analyze connective principles as conditional random quantities within the theory of logical operations among conditional events. So this is the second approach. In approach 2, a basic conditional is a conditional event instead of a conditional probabilistic constraint, which is a 3-valued object, so true, false, and void. Logical operations among conditional events yield not conditional events, but conditional random quantities with more than 3 possible values. We will see an example later. And of course, you must not nest conditional probabilities, but you can do that with these conditional, with these logical operations among conditional events. So the definition of the second approach of the validity of the connective principle is very elegant compared to the first one, because this is one definition which suits all the connective principles we consider. A connective principle is valid if and only if the associated conditional random quantity is constant and equal to 1. So this is the important definition. So now let's have a look at how to interpret the conditional event as a conditional random quantity. Given an event A, we denote by the same symbol in its indicator, which is equal to 1 or 0, according to whether A is true or false. Let P be the assessment on the conditional probability A given H, be a conditional probability assessment on this conditional event. The indicator of A given H, which is denoted by the same symbol, is defined as the following random quantity. So A given H is defined in this way, and it is 1 if A and H is true, it is 0 if not A and H is true, and in some sense you get your money back if the conditioning event is false. So these are the usual conditions. Of course, the third value of the random quantity depends on the assessed probability of the conditional probability. Now, a conditional is interpreted as a conditional event where, or we have this equation here. We interpret, it is not the case that if A then B by this formula here, the negation of the conditional event is defined simply by the 1 complement. And now we can prove the validity of Aristotle's thesis. We interpret Aristotle's thesis, this is this formula, by this object here. And then as this one holds in general, we obtain that Aristotle's thesis is constant and equal to 1 and therefore validated. In a similar way, we also validate Aristotle's thesis prime. For Abelard's thesis, we interpret Abelard's thesis, this is this one, with this object here. And this is a conditional event because we condition always on A. So in this case, it is in some sense a bit simpler. Of course, we assume that the conditioning event is not the contradiction here. We observe that this formula here, this conditional event here, reduces simply to the empty set given A, which is of course 0, and then the negation of this becomes 1, and therefore Abelard's thesis is validated. For studying Aristotle's second thesis, where the conditioning events differ, we need to have a definition of conjoined conditionals as conditional random quantities, which I present very quickly here, and more, you will learn more about this by Giuseppe's talk at the end of the week. So given any pair of two conditional events, A given H and B given K, with the corresponding assessments X and Y, the conjunction is defined in the following way. We have these 5 conditions here. So in the betting framework, you agree to pay the value set for the provision in this object with the proviso that you will receive 1 if both conjuncts are true, if both conditional events constituting the conjunct are true. You get 0 if at least one of the conditional events is false. You get the probability of that conditional event which is void if one conditional event is void and the other one is true. These are these 2 conditions here. And you get the quantity, you get your money back if both conditional events are void. So this is the definition of the conjunction of 2 conditional events. And this allows us to interpret this object here. This is Aristotle's second thesis, because this is the conditional random quantity B given. It is not the case that B given A and B given not A. And here we get these semantics here, which is not constant and can therefore not be necessarily equal to 1. And in particular, for example, if you choose that X and Y is 1, which is coherent, you get this one reduces just to not B, which is not necessarily equal to 1, as it could be either 1 or 0, depending on whether B is not B is true or false. And in a similar way, we can go through these connective principles. Therefore, Aristotle's second thesis is not valid. For the iterated conditioning, we also need a definition of iterated conditionals. And recall the definition of the conditional event, which is given here. So true, false, and void, if you like. And the structure of the definition of the iterated conditional is in a very similar way. So instead of having here A and H, we have here conditionals, box and circle. And then we see the definition is the same, obtains the same structure as the definition of the iterated conditional obtains the same structure as the definition of the conditional event up here. Sorry, where is it? Here. So this is the same structure as what we have here, with the difference that here we have conditional events and here we have atomic conditionals. Atomic events. So in explicit terms, we obtain the definition of the iterated conditional here, B given K, the whole thing given A given H, and we have these 7 conditions here. And these 7 conditions are, of course, much more complicated compared to the 3 conditions that we have for the conditional event. But this is necessary in order to avoid Lewis's triviality results. So with this semantics, we can validate Bourdieu's thesis, where Bourdieu's thesis, this is this one, if A then B, then it is not the case that if A then not B, is interpreted by the iterated conditional, the negated conditional not B given A, this one is negated, given B given A. And going through all these details, we obtain that by coherence, it must be that the value assessed here is 1, and therefore, this object is constant and equal to 1, which validates Bourdieu's thesis. Here is an overview of all the connective principles we considered in the second approach. Here you see whether they are valid or not. You can see all of them are valid except for Aristotle's second thesis, and also the Bourdieu's variation number 3 and 4, they are also not valid. And here you see the interpretation in terms of conditional random quantities. Here you see the connective principles. And with the contrasting this with the first approach, we note that RBT and RBT prime are not valid in approach 1, whereas here they are valid. So this brings us to the concluding remarks. Connectivity, this idea that self-contradictory conditionals should be false, is not only psychologically plausible, but also emerges naturally under probabilistic interpretations. Specifically, we recovered various connective principles via 2 approaches. Approach 1 interprets connective principles by defaults, which are interpreted by probabilistic constraints and conditional events. That is, basic conditionals are interpreted by probability constraints, and negations, that the assessment is negated, and we use the wide-scope negation. In the second approach, connective principles are obtained by logical operations on conditional events. The basic conditionals are interpreted by conditional events. The negation of the object is negated, and by the narrow scope negation. We showed that Aristotle's second thesis, basis variations 3 and 4, are not valid in both approaches. And we also aim to show that, let me also mention that coherence-based probability logic allows for bridging qualitative and quantitative principles, and applications include, for example, we developed some semantics for Aristotelian syllogisms, for the squares and hexagons of oppositions in terms of probability and defaults. There is a lot of work on non-monotonic reasoning, like on system P, or on weak transitivity and other rules. And we also obtained some results concerning aversion for the towards a deduction theorem using this idea of logical operations on conditional events. On the paradoxes of the material conditions, they are blocked by the semantics. And there are many experiments in the psychology of reasoning, and so on. So future work concerning this is also to analyze other connective principles, and we are happy and interested if you have any suggestions to generalize what you do. Thank you very much for your attention.
Okay, thank you very much, Nikki. And okay, now if there are any questions from the audience or also from the online attendance, you can raise your hand in the chat. Okay, well, yeah, there is somebody in the audience.
Yes, a question. I will ask a rather sarcastic question. Nikki, do you still believe that your paper you cited on slide 1, which has been in press for the last 9 years, will be published?
Which paper?
You cited on the first slide that it is 2012 in press.
No. This is the style is here. This means this is one paper which was published in 2012, and this is another one which is currently in press. So these are two different papers. Otherwise, I would have written instead of the comma, which is in press, right? And that would be really odd.
Okay, we have a question, an online question from Luis Godot. Luis Godot?
Yes. Hi. No, I was wondering about this. I think you mentioned at the very end this list of connective principles that are satisfied and are not satisfied. So, what about the ones which are not satisfied by either of the two approaches? What do you think? I mean, what is wrong there? Are the principles that are wrong or the interpretation?
Let's have a look at just a moment. Let me share the screen again. So these principles are inspired by logic, right? Logicians are using, for example, so-called Aristotle's second thesis, and from our point of view, this is just mistaken, because if you conditionalize on A, right, on the one hand, and you conditionalize on not A, well, they are completely different things, right? So therefore, you cannot make a connection to say no. You cannot hold them both at the same time. So, from our point of view, this is an example where really there's something wrong with the connective principle.
Okay.
But for some reason, if you have a different semantics, right, like people do, like modal logic or what have you, maybe it makes sense for them. But for us, it simply does not make sense.
Might be a causal element assumed in Aristotle's second thesis, that it's not possible for A to cause B and not A to cause B.
Right.
That or something.
that could be an explanation of why you want to have such a principle. But from our point of view, if you want to have some, if you have some implicit assumption, right? If you want to validate this, then you need to make some more connection. You need to add some more information. Then you might obtain something. Like we studied, for example, if you have transitivity, right? If A then B, if B then C, therefore if A then C, this is non-informative, meaning whatever premise probabilities you have, you always get 0, 1.
Yeah.
But if you want to have this kind of transitivity, you can add some information, either it be logical or some probabilistic constraints, and then you can draw sensible inferences.
Okay, thanks.
Thank you.
Okay, so I think this is all the time we have, but okay, we thank all the speakers again, and of course everybody participating from the audience. And now I think there is a coffee break for half an hour, so okay, we will be seeing you later. Thank you.